If, as according to Merriam-Webster's dictionary, the definition of the word invent is to produce something, such as a useful device or process, for the first time through the use of imagination or of ingenious thinking and experiment, then Nikola Tesla did not invent the induction motor. Tesla played a role in the development of the motor, and that is certain. The role, however, was not a large one. The modern world began with the invention of the rotating magnetic field by Galileo Ferraris sometime in the late 1880s. This rotating field is the heart of the induction motor. Two other early electrical engineers, Mikhail Dobrovolsky and Charles Eugene Lancelot Brown, have claimed to similar concepts. So, although Nikola Tesla didn't invent the induction motor, he did, however, have the foresight to patent this invention. To understand the importance of the induction motor, we need to look back to the Industrial Revolution of the 18th century. At that time, the dominant prime mover was the steam engine. Steam engines drove the majority of the industrial processes. From paper mills to huge blast furnace blowers. In some heavy industries, steam engines were rated in thousands of horsepower. Many continued in use into the 1930s. A line shaft mounted above the production floor and running the length of the plant was used to transmit the power from the steam engine to the production machinery. This power was distributed by means of takeoffs. These takeoffs were in the form of pulleys that drove chains or belts to power such loads as looms, runout tables, cranes, pumps, fans, and machines of all types. As time went on and the number of driven machines increased, so did the losses due to friction. As much as 80% of the power was lost in transmission. By the latter half of the 19th century, it had become obvious that there was a need to find an alternative to mechanical drives. At about that time, the idea of using an electric motor was being discussed in engineering circles. Edison opened his Pearl Street station in 1882. This station was intended to supply electric power to electric lamps. The original station's lighting load grew rapidly. Several competitors soon entered the lighting field. In short time, it became apparent that there was a utilization problem. As the load curve shows, the majority of lighting equipment was not in use during the hours of daylight. In this winter graph, we see some home lighting being used around 5 a.m. and then drop off after 10 a.m. A more or less continuous load would exist from 10 a.m. to 6 p.m. This afternoon load was composed of power to industrial lighting, typically arc lamps in the industrial plants and incandescent lamps in the offices. This load would again peak in the evening hours and start to decrease at bedtime. Any load that occurred during the early morning hours would be street lighting and a very few industrial loads that were continuous, and very little else. A problem that faced electrical system owners occurred between 10 a.m. and 6 p.m. This is the period when the generators were lightly loaded. During this period, heat loss from the steam engine and the boilers remained about the same as at full load. Although this expense was not welcomed, this was necessary to prevent the additional fuel cost incurred when restarting a cold boiler. In addition, the cycling of heating and then cooling the boiler parts caused their own maintenance problems. What was needed was a load that would draw power during this off time so that heat was not wasted. To accomplish this, lighting plants began to promote the use of electric motors. A motor load added to the lighting system, shown in red, would increase the overall utilization and result in a greater return on investment. The need to improve the load factor was a major stimulus in the development of industrial electric motors. This also was about the time that industry was looking for a replacement for the low-efficiency steam engine. The electric motor would be the answer. According to the Report on Manufacturing Industries in the United States, 1890, the kilowatt capacity of electric plants was as follows: 1,300 kilowatts of arc lights, 12,850 kilowatts of incandescent lights, and just 976 kilowatts of motor power. Motors amounted to less than 5% of the total generated load. Because Edison's direct current lighting system was the dominant power system of the 1880s, the most common motor of that era was a direct current motor, the shunt motor. Early examples bore little resemblance to motors of today. The efficiency was low and resulted in part from a poor understanding of the magnetic circuits of the motor. But the need to supplement the lighting load soon drove improvements in these machines. To better appreciate the importance of the induction motor, we should be aware of how a motor works in general terms. All motors produce torque by the interaction of two magnetic fields, one produced by the stator and the other by the rotating armature. These names can be confusing because they were developed before motor action was fully understood by the average engineer. The stator field is produced by the field poles and is commonly referred to as simply the field. The rotor field, produced by the armature, is not typically referred to as a field. The shunt motor has its field, the stator, and the armature, the rotor, in shunt, or more commonly called parallel. The shunt motor has the desirable feature of a nearly constant speed as the driven load increases. This mimicked the action of a governor-controlled steam engine, and as such allowed the production rate at each workstation to remain nearly constant as load increased or decreased. The DC motor, however, has two serious problems. One problem is its commutator. The commutator is actually a mechanical rectifier that changes direct current from the supply system to alternating current in the motor armature. In this schematic diagram, the commutator is shown diagrammatically as a circle. The stator field is represented by the letter F, and the armature is represented by the letter A. The half-moon squares on either side of the commutator represent the brushes that connect the rotating armature conductors to the stationary supply voltage V sub S. Both the armature and the field are powered by the supply voltage. In other words, they're in parallel. This was also commonly called shunt connected. The armature shown here has been removed from the motor stator. The commutator is attached to the rotor shaft. It is made up of several conductor segments that are not shown in the previous schematic diagram. These segments are in turn connected to the armature conductor windings. These windings were attached to the surface of the armature drum in early machines, but later were laid in slots formed in the armature drum. The weak point of the DC motor is its commutator. It's used to switch the connections of the rotor in order to maintain the right angle relationship between the electromagnetic field of the rotor to that of the stator. Because the commutator switches the armature current, sparking will occur. This sparking erodes the commutator segments, as shown here, requiring frequent maintenance. While the details of this magnetic interaction are outside the scope of this presentation, it's important to understand that the commutator keeps the armature's magnetic field at right angles to the field produced by the stator's poles. This 90-degree relationship produces the maximum torque for a given strength. The other problem with DC motors was the direct current system itself. There is no simple means of raising the DC distribution voltage. As transmission distances grew, this limitation meant that the Gallard-Gibbs Westinghouse AC system, which used transformers to increase the transmission voltage and thus reduce the electrical current, would be the system of the future. The problem, however, was that there was no AC motor that had the stable speed characteristics of the DC shunt motor. For those who would solve this problem, there would be a large and profitable market. The solution was the induction motor. Shown here is a photo of Tesla's motor. This may be the motor he exhibited at his 1888 AIEE paper, A New System of Alternate Current Motors and Transformers. It's obvious from this photo that his motor bears little resemblance to an actual induction motor. A closer look at his paper and patents will help us understand what Tesla knew about the induction motor and how it should operate. But first, we need to understand how an induction motor works, how it produces torque by the interaction of two magnetic fields, one from the stationary part, commonly referred to as the stator, and one from the rotor. In a typical induction motor, the field, the stationary part, induces a current in a rotor that produces the rotor's own magnetic field. A property of magnetic fields is that two or more will tend to align themselves into one stronger field. Since the rotor is the only part that can move, it does so in the direction shown. The basic rules governing the action of magnetic fields have been known since first described by Hans Christian Ørsted in 1820. Tesla's patent should account for this motor action in one form or another. Let's see what he has to say about this. The first patent we'll look at is US 381968, electromagnetic motor, dated the 1st of May 1888. Note that the date the application was made is the 12th of October 1887, and the date that the patent was granted is the 1st of May 1888. All three patents that we'll look at were granted the 1st of May 1888. However, the application date is used by Tesla in the body of the patents when referring to other patents and not the date granted. This can cause some confusion when trying to compare one patent to another. The second patent is US 382280, the electrical transmission of power. These two patents are very similar in content, even though one is for a motor and the other for power transmission. The third patent is US 382279, electromagnetic motor. It's different from the other two in several respects. If Tesla did invent, or at least patent, an induction motor, then we should see statements relating to an induction motor in his patents. Before we have a look, we need to understand what the characteristics of an induction motor are. Two characteristics are fundamental to induction motor operation: a rotating magnetic field and a drooping torque speed curve. The phrase drooping means that as the load torque on the motor increases, the speed drops off from no load to a point where it can no longer drive the load and the motor stalls. This drooping load characteristic is what we're looking for. If Tesla's patents don't show this, then it's not an induction motor that he's describing. First, we'll look for the mention of a rotating magnetic field in Tesla's patents. The production of a rotating magnetic field is an important aspect of induction motor operation. In US 382280, we see the phrase magnetic poles constantly shifting or whirling around the core. In other patents, there is a similar language. The patents also provide diagrams to show how this would work. This diagram gives a good graphic presentation of field rotation and will be used here as representative of Tesla's motor concept. In the left column is shown an alternator, and in the right column is the motor stator or primary winding connected to the alternator by conductors not shown in the diagram. The alternator's armature rotates between north and south field poles. An armature is that part of an electrical machine that carries alternating current. Although the alternator in this patent is not representative of a modern alternator that has a stationary armature, a rotating armature was standard for that time period. As the alternator armature rotates from Figure 1 down to Figure 8, as shown here in Tesla's patent, an alternating voltage is generated in the rotating windings. The resulting current from the alternator coil B produces a field in the stator windings of the motor, shown here as CC in the diagram. The motor field rotates as a result of the alternator's rotation. In other words, the field poles of the motor stator turn clockwise, one revolution of the motor for one revolution of the alternator's armature, just as if they were connected by a solid coupling between the two. This phenomenon is sometimes referred to as an electric coupling. The patent's Figure 9 shows a wiring diagram of the motor circuit with the rotor disc D of the motor. The phase conductors are connected between the motor's stator and the alternator G. Although this shows that Tesla did patent the rotating magnetic field, in his early work he doesn't actually use that phrase. It's clear, however, that a rotating magnetic field is what he's talking about. Do any of these patents mention a drooping speed curve? A closer look at these patents will help us understand what Tesla knew about induction motor theory. US 381968 talks about uniformity of speed irrespective of its load within the normal working limits. US 382280 uses the same phrase. So here's one aspect of the patents that doesn't support Tesla's invention of the induction motor. Uniformity of speed is not a characteristic of an induction motor. As we've seen, the speed of an induction motor drops as the load increases. In patent US 381968, Tesla refers to Figure 9, where he says on line 36 of page 4 that the disc D has a tendency to follow continuously the points of greatest attraction, and since these points are shifted around the ring once for each revolution of the armature of the generator, it follows that the movement of disc D will be synchronous with that of the armature. This is a synchronous motor he's describing, not an induction motor. With US 382279, however, things are different. Tesla says on page 1, line 32, I have discovered that advantageous results may be secured in this system by utilizing the shifting of the poles primarily to set up currents in a closed conductor located within the influence of the field of the motor, so that rotation may result from a reaction of such currents upon the field. Page 2, line 104, we see the statement, when these motors are not loaded but running free, the rotation of the armature is nearly synchronous with the rotation of the poles of the field, and under these circumstances, very little current is perceptible in the coils E, E'. But if a load is added, the speed tends to diminish, and the currents in the coils EE are augmented so that the rotary effort is increased proportionately. Here, Tesla is describing the drooping characteristics of an induction motor, although he does not actually call it that. For whatever reason, it seems that Tesla has finally realized that an induction motor, and not a reluctance motor, is what he should be patenting. Yet in the fourth document we're referencing here, his paper to the AIEE on the 16th of May 1884, a new system of AC motors and transformers, he is not focusing on the attributes of an induction motor. The title, for instance, still includes transformers. On page 320 he says, if it is desirable to secure a constant speed and at the same time a certain effort at the start, two armatures, one for torque and the other for synchronism, may be fastened on the same shaft. Then on page 322, talking about a motor that can be used for various speeds, Tesla says, in a general distribution system, the central station generator should be provided with a considerable number of poles. The motors operating from this generator should be of the synchronous type, but possessing sufficient rotary effort to ensure their starting. It will be advantageous to provide each motor with a greater number of pole projections or coils. By simply changing the connections, the motor may be adapted to any probable demands. So, what should we take away from this long-winded video? Well, I think the most important thing to understand is that the induction motor, more than any other device, was the cornerstone of the Industrial Revolution of the 20th century. A secondary takeaway is that Tesla was not aware of what he was patenting. His AIEE paper especially shows that he felt that the induction motor should be used as a transmission line receiving motor and not something that would be used right at the industrial machinery. His rotary disc would have melted due to eddy currents, and his use of salience poles would have produced harmonics that would have crippled motors of ratings above 1 horsepower. A great deal more work was to be done on the induction motor. This work was not done by Tesla. Westinghouse chief machine guru Benjamin Lamy would be the one to bring it into the next century. Tesla had already moved on to wireless power transmission and death rays by that time.